Okay, I want to revisit the Atwood's machine, and I have here taken a particular Atwood's machine with a 1 kilogram and 2 kilogram masses hanging from the two strings. And I've already solved this problem once, so I'm not going to solve it in detail, or at least I solved one like it. And so you might want to pause the video here and make sure that you understand what the solution is. But basically the solution is that the acceleration is that the 1 will accelerate up and the 2 will accelerate down with an acceleration of 3.33 meters per second squared, and the tension in the string will be 13.33 newtons. What I'm interested in now is if this thing is, say, hanging from the ceiling, what is the force that you have to exert in order to hold it up? In other words, suppose that this thing is supported by a string that goes up to the ceiling. What is the tension in this string? Okay, so we choose a body, and I will choose the pulley as the body, and then I'll say what are all the forces on the pulley. And well, we know that there is a tension 13.33 this way, and there is a tension 13.33 this way, and there is some unknown force, call it F, which points up. And I want to know what F is. Well, the pulley's in equilibrium because it's not accelerating. So the sum of the forces on the pulley has to be equal to 0. And so that's got to be equal to F minus 26.67. In other words, F is 26.67 newtons. Okay? All right, now I want to disconnect this Atwood's machine from the ceiling. And I want to grab onto that string, and I'm going to pull up on it. Okay, so let's start this whole problem all over again. I'm going to pull up on it with a force of, let's say, 30 newtons. Okay? All right, choose a body. Well, I will choose the pulley again first. Okay. So I'll come down here. Okay, choose the pulley as the body. And what are all the forces on the pulley? There is the force that I'm exerting, which is 30 newtons up. And there is some new tension in the string. It won't be the same anymore, because only if this is 26.67 newtons is that force up. Okay, and so now what I want to say is the pulley accelerating? Well, yes, the pulley is accelerating, but we have assumed, even though it's not really, can't really possibly be true, we've assumed that the mass of the pulley is 0. What that means, of course, is we have assumed that the mass of the pulley is very small compared to 1 or 2 kilograms. And if that's the case, then the sum of the forces on the pulley in the y direction, let's call this plus y, sum of the forces in the y direction is equal to 30 minus 2t. In other words, the tension is now 15 newtons. So now we can ask, what is the acceleration of each of these two objects? Well, you see, now their accelerations are not going to be the same. Okay. For example, you can imagine pulling up with just the right force. If they both started at rest, you could imagine pulling up with just the right force so that the 2 kilogram object stayed at rest and the 1 kilogram object accelerated up. Okay, so let's find out what they are in this case. Okay, so we go and we choose, I guess this is the 1 and this is the 2, okay? And actually I'm, I'm just going to choose, we don't have to do the rule of the finger here. The reason we don't have to do the rule of the finger here is because these guys don't have the same acceleration anymore, so we don't have to worry about that. We just let everybody have a plus y up. So for this guy, what are all the forces on this guy? Well, let's go here, and so what are the forces on him are the tension in the string up, which we now know to be 15 newtons, and this guy's acceleration, or weight down is 10. So the sum of the forces in the y direction is equal to 15 minus 10, which is equal to 5, and that's equal to m times a sub 1. So this guy has an acceleration up of 1 meter per second squared. I'm sorry, of 5 meters per second squared. Okay. And similarly, this guy, forces on him are 15 up and 15 up and 20 down. So the sum of the forces in the y direction is equal to 15 minus 20, or minus 5 meters per second squared, and that's equal to a of the 2 kilogram object. So when you first look at this, it's sort of intimidating because the two have different accelerations, and it looks like it's going to really be a hard problem. But as a matter of fact, as you can see, it's actually easier than the problem where you would just simply tie it to the ceiling. Okay, so that's the end of that Newton's second law example.